And you have the recording.
Yes.
Okay, good. Okay, so thanks everyone. I think this is a nice result that actually obtained by some of our students. And I think I'll start the talk and then other
Good morning, everyone, and thank you for coming. Today we are going to present our recent work, to approximation for price collecting Steiner forest, and which is as Mohammad said, is a collaboration of me, Ali Ahmadi, Iman Gholami, Peyman and Mohammad Mahlavi, supervised by Professor Hajiaghayi. An overview of this talk is, first I'll go through a brief introduction of the problem, what the problem is, and after that, our idea on two approximation algorithm for Steiner forest and a tree approximation for price collecting Steiner forest, and finally, our main contribution, which is a two approximation algorithm for price collecting Steiner forest. Okay, let's start with the basics, and you probably know Steiner tree. It's a generalization of minimum spanning tree problem. And in this problem, more than honestly, we have a set of vertices called terminals. And the objective is to connect all terminals. Basically, we choose a subgraph of the given graph with minimum total edge weight such that all the terminals are inside that graph and connected. And the next problem is Steiner forest, which is a generalization of Steiner tree problem. In this problem, instead of terminals, we have pairs of vertices called demands. And the objective is to choose a graph such that with minimum total weight such that all the demands are in the same connected component. So for every demand, both endpoints should be in the same connected component. And the next step actually is price collecting Steiner forest problem, which is an advanced variation of a Steiner forest problem. In this problem, each demand has an associated penalty. And as we are choosing the subgraph, we can decide either to satisfy a demand, it means that both endpoints of that demand are in the same connected component, or pay the penalty for that pair. And the subjective is, again, to minimize total edge weight, but plus all the penalties that we pay. And before going to our work, let's see what others have done around this problem. Well, there is a 1.39 approximation for Steiner tree problem from stock 2010, a 2 approximation for Steiner forest from 92, and a near 2 approximation for price collecting Steiner tree. And let me quickly introduce the problem price collecting Steiner tree. It's a specification of price collecting Steiner forest, but in this problem, all the demands have a common vertex. So there would be actually one connected component. And also there's a tree approximation for price collecting Steiner forest using primal dual approach and a 2.54 using randomized LP rounding. And interestingly, there is a result showing that the integrality gap for this problem, price collecting Steiner forest, is 2.25. And finally, our contribution is proposing a new idea. We call it coloring schema. Using this idea, we can reinterpret the 2 approximation algorithm for Steiner forest and 3 approximation algorithm for price collecting Steiner forest with a slightly modified, and our primary contribution is the two approximation algorithm for price collecting Steiner forest. In this work, actually, we did improve the 2.54 approximation factor for this problem and also beat the 2.25 integrality gap. And also it closes the gap between price collecting Steiner forest and Steiner forest, which is a specification of that problem.
You say the story of that? I mean, you should say the history of the Steiner forest and price collecting.
Yeah, I showed some papers.
Yeah, see, but price collecting Steiner tree also was there in that paper. So that is important. The approximation of the Steiner forest. Paper that has two approximation of Steiner tree. So that like on find the
The next is to approximate Steiner forest, and Iman will explain this.
Okay, hey, today I'm gonna tell you how we can utilize our coloring schema in order to give a two-approximate solution for Steiner forest. And the part of our color schema, actually one part of that is static coloring. In the static coloring, we consider our graph edges or curves with the same length as its cost. And during our process of coloring, we maintain three variables. The first one is a forest, which is initially empty. And by the end of our algorithm, it's going to be our solution. Next, we maintain the connected components of F, and active sets are a subset of connected components which are active. By active, we mean that there is a vertex in that connected component which is not satisfied yet. It means there is a demand that needs to be satisfied later and needs to be connected to another vertex. And in every moment of our algorithm, active sets coloring their adjacent edges and in order to connect the demands. So we know that each active set has its unique color, and they start coloring like here. They start coloring its adjacent edges, and once an edge is fully colored, or we say it gets tight, we add that edge to our forest, and we merge the components of its vertices, and we do the same in the actives. I missed something. Active sets, connected components initially are the vertices of the graph. Each connected component is one vertex, and the same for active set, but only vertices which is in a demand are active. Like this black node is not active. And when active set grows, we merge. When an edge gets tight, we merge the two components and two active sets if there's two. And after that, we check if that active set is satisfied, which means all the demands this active set participating is satisfied. For example, here we had two vertices, which was a demand, and when it's satisfied, it doesn't grow anymore. So we keep doing this until all demands are satisfied. And then the resulting coloring, which is something like this, we have these edges in our forest, which is actually the same here. And at the end of the algorithm, we probably buy some edges, which is not necessary for us. For example, this edge doesn't help to satisfy any demand. So we remove them. So the resulting forest is something like this.
What are the demands?
Demands, actually, Ali told us, demands are pair. Oh, okay.
Here they are not here.
Yeah, they are shown by colors.
So
Two
what are the
greens,
ones that don't have the color?
because it's going to be very colorful. That's disturbing. It's yeah, yeah, probably.
You can label that in-
Okay, sure.
Color is good, but you can have it.
Yeah. Okay. So in order to analyze this algorithm, I'm going to define a variable ys, which is the duration that active set S colors some edges. First, we show that the total duration of coloring edges is less or equal to optimal. It's not that hard if you consider a moment that an active set coloring some edges. We know that there is a demand which is not satisfied yet. So in the optimal solution, we know that there is a path between this vertex of this demand to another vertex. So there's an edge that goes out from this active set since it's coloring edges. On the other hand, if we prove that our algorithm is less or equal to 2 times total duration of coloring, then we can say that our algorithm is a 2 approximation algorithm. It's not that hard to, if you take a look at every moment of our algorithm, there is some active set that coloring edges. We know that the number of edges that we're coloring is equal to the degree of our active set. For example, here in S1, we color like 3 edges, which is the degree of that active set. And also we know that the leaves of the final forest are active because if they are not active, we know that there's a leaf and one edge goes out from it. So we can remove that edge. It's a redundant edge. So we know that all leaves are active. And using this, we can conclude that the sum of degree of all active sets are less or equal to 2 times the number of active sets that we have. And since we know that F is fully colored, if we take a look at the whole process of coloring, we can say that the edges that we are fully colored is actually this amount at every moment contribute to our algorithm. And on the other hand, at every moment, the duration of coloring is equal to the number of active sets. So this amount contributes to the total duration of coloring edges. So we can obtain this inequality. So it's a 2 approximation approach. Yeah, I think the time is like a little bit less for that. It's not enough. Yeah. Yeah, we have. And Peyman is going to represent a reapproximation solution for a price collecting Steiner for us.
So I want to use this coloring schema that we had and achieve a 2 approximation algorithm for price collecting Steiner forest. So in price collecting version of Steiner forest, we have a penalty for each pair, and we can pay the penalty and don't connect the endpoint of that pair. Okay, so it means that if we are spending more than the penalty of a pair to connecting it, it doesn't make sense. We can just pay the penalty and don't connect it. Okay, so we want to define a new coloring that apply this constraint on that new coloring. So we define this new coloring dynamic coloring. So I'm referring the coloring that Iman said for Steiner forest as a static coloring, and this new coloring is dynamic coloring. Okay. So in the dynamic coloring, we have a unique color for each pair, and we want to add some limits for each color. So we say that we don't use a color of a pair more than the penalty of that pair. Yeah. So this dynamic coloring, the process of coloring, this dynamic coloring and static coloring are almost the same. So at each moment, active sets are coloring the adjacent edge, and the only difference between the static coloring and the dynamic coloring is that the color they are using. Okay? So the problem with the dynamic coloring is that in our process of coloring, we say that active sets are coloring the adjacent edge. So in the dynamic coloring, since each pair has a unique color, we don't know which color we should use at each step. I mean, each active set has a lot of pairs inside it. I mean, we don't know which color we should use at this step. So we want to use our static coloring to achieve a dynamic coloring. And the reason that we use name dynamic because the color of each edge is changing during the algorithm. It's not consistent. So now we say that we want to achieve a dynamic coloring from the static coloring that we have. I mean, at each moment we have an instance of a static coloring, and we want to construct the dynamic coloring from it. So what does it mean? It means that I want to assign each moment of coloring in the static coloring, each moment that we use color, for example, S, to a pair I and J in the dynamic coloring. So we define a new graph here to find this assignment. So in this new graph, we put one vertex on the left side for each subset of the vertices of the original graph. So these vertices, I mean, they are showing the set of the subset of the vertices of the original graph, and we know that in the static coloring, each set of the vertices has a unique color. I mean, each vertex in the left side show one color in the static coloring. Okay, and in the right side, we put a vertex for each pair of the original graph, pair of the vertices of the original graph. So this vertex shows one color. Each vertex shows the one color of the dynamic color. Okay, and then we added one vertex named source, and for each set we add an edge from source to that set, and the capacity of that edge will be the amount of the duration that we used color S in the static coloring. And also in the right side here, we add edge from each pair to vertex sync, and the capacity of this edge will be the penalty of that pair. And finally, we add the edge from each set to each pair. If that set cut the pair, I mean the endpoint of this pair, one of them should be inside the set and one of them should be outside the set. And the capacity of this edge will be infinity. So now we use this graph and we run max flow on this graph to find our assigned. Okay. So what is the max flow show in the graph? So in the left edge in here, the flow that come from source to each set S shows the duration of the coloring for the set S in the static coloring, and we want to it become it will be equal to the YS. I mean because we want to assign every moment of the coloring in the static coloring, so this edge should be filled. I mean the amount of flow should be equal to the capacity. And the middle edge, they are showing the assignment from static coloring to dynamic coloring. So the amount of flow from set S to pair IJ shows that I want to assign the color of the color of the S to pair IJ with this amount. And finally, the edge in the right side shows the amount of the color that assigned to pair IJ, and it won't be more than the penalty of the pair IJ. The constraint that we wanted is happen here. So, okay. Now we showed that how we achieve the dynamic coloring from static coloring, but still it doesn't have any effect on the static coloring. I mean, we should apply both of this coloring to, affect both of this coloring together. Okay, So in the static coloring, as Iman said, each time that an edge becomes fully colored, we measure its endpoint. Okay. So in the dynamic coloring, we want to see how these penalties will affect our algorithm. Okay. So so we want to in the previous max flow that we find, so it's possible that in some step of algorithm we have a static coloring that it's not possible to assign every moment of them to dynamic coloring. Okay, so we want to see when an instance of static coloring will cause a problem for us. Okay. Here we define a pair tightness. So what is the pair tightness? It means that color of a pair, we run out of color of a pair, and we cannot use the color anymore because of the constraint that we had. We don't want to use the color of a pair more than its penalty. So yeah, we define pair tightness. I mean, a pair, we call it tight if we cannot use its color anymore. And when a pair got tight, it means that if we continue the process of coloring, the process of static coloring, we will achieve an invalid static coloring. It means that we cannot run find the max flow that satisfy every edge on the left. That means that it cannot assign every moment of the static coloring to dynamic coloring. Okay, so when we have a tight pair, we decide to pay the penalty. We don't, because we ran out of the color for that pair. We don't want to continue to color with that pair. We pay their penalty and remove their demands. We don't assume that we have these demands anymore, and we continue the process. So we continue this process until the end of the algorithm. We don't have any active set, and so at the end of the algorithm, we will achieve the last dynamic coloring that we have. And so in that dynamic coloring, every pair that they color is fully used. We pay their penalty, and then for other pairs, we should connect them similar to what we had for Steiner forest. And so this will give us a T-approximation algorithm. And we're almost done. We just add another step to this algorithm. So this final step doesn't change the approximation factor, but we need it for the T-approximation algorithm that we design in the next step. So in this final step, we only try to minimize the number of the pairs that we are going to pay their penalty. Okay, so as I said, we only pay the penalty for pairs that were tight. Okay, so here we check if there is a pair, for example, IJ that is tight, and if there is a pair IPM and JPM that is not tight, and if we can pass the flow, epsilon flow from that is passing from pair IJ to pair IPM JPM. So here, for example, in the left side, we have the base flow, and we change it here. Okay. So with this operation, we reduce the number of tight pairs by 1, and we do this operation until we cannot do it anymore. So at the end, the number of the tight pairs are minimal, and we pay for every tight pair, to pay the penalty of every tight pair, and connect others. So now Mohammad will show how we use this algorithm to achieve a T-approximation algorithm.
I will now explain how we achieve a T-approximation using our algorithm. So in our algorithm, we first run the T-approximation algorithm that Peyman mentioned, and we get a solution from that. If there are no penalties paid by that solution, we just return that solution, and we will argue later that that is a T-approximation. If there are some penalties paid by that solution, we set all the penalties for those pairs to 0, and we get a reduced instance, and we assume that we will pay those penalties in any future solutions, and we just recursively run the algorithm. And we get another solution this way. And we compare these two, we report the one with the lower cost. Now, so in our analysis, we will now have these two solutions and we will return the one, the minimum cost. And we want to compare the cost of these solutions to the optimal solution opt that we consider. And this will improve our approximation ratio from the tree approximation in one of two ways. We either get a better bound for the optimal solution, or the cost will be significantly reduced. The optimal solution cost will be significantly reduced in the reduced instance. And that will give us a better approximation in the second solution. Okay, now in our analysis. Yes, we basically consider a number of solutions, but recursively we get two. But if we consider it like as we go on, we get one solution, we repeat until we have at some point we have no penalties paid. And we consider a minimum of all of these solutions in a way, but we can also look at it recursively with just two solutions.
Yeah, but I think it's better to present the algorithm in a natural way and then I'm not sure, but then we can talk about the analysis that this way we are
analyzing it this way, but yeah, we can also introduce it in that. Right. So in our analysis, we first classify the demand pairs into 4 categories based on whether our first solution that we obtain in the algorithm connects them or pays the penalties for them, and based on whether the optimal solution opt connects them or pays the penalties for them into these 4 categories. And we also do this notation for the total duration of coloring in each of these sets of demands. Oops. So for example, for CC here with big letters, capital letters, we use the small letters CC to say the total duration of coloring for those pairs that fall in this. And we introduce this notion of single edge and multi-edge sets, which we classify all the sets active sets that can color around them by how many edges of the optimal solution are incident to the active set. So how many edges of the optimal solution are cut by that set. It may be 0 for some active sets, but we don't care about that in the rest of our analysis. And we define single edge sets as the ones that cut only one edge of the optimal solution, and multi-edge sets as the ones that cut 2 or more edges of the optimal solution. So here, for example, this set cuts only this, if this is the optimal solution in the background, this set cuts only this one, and this other set cuts 2 edges. So this is a multi-edge set, and this one's a single edge set. So now we try to divide the coloring time for some of our sets. First, we note that there are no 0-edge sets cutting pairs that are in CC and CP, because these pairs are connected by the optimal solution opt. So there will be a pass going from the connecting the endpoints of these pairs. And for any set that cuts one of these pairs, that there will be an edge of the optimal that cuts that set. So it'll be either a single edge set or multi-edge set. And we divide the coloring time for the pairs in this set into 2 parts. The first is the coloring time we have for single edge sets that cut these pairs. And it's the dynamic coloring time for these pairs in combination with the single edge sets. And we also define that for the multi-edge set. And why this is important for us is because when you have a multi-edge set coloring the graph, it colors 2 edges of the optimal, at least 2 edges of the optimal at the same time. So that'll help us get better bounds. And we note that because of there being no 0-edge sets, we have this equality. No 0-edge sets connecting these pairs. Okay, now we try to get our lower bound for the optimal solution. We note that for the connected pairs, we can bound the forest selected by the optimal solution using the coloring on the edges of the forest. So we know that for each set cutting one of those pairs connected by the optimal, we have an edge of the optimal. Wait, I got confused. Sorry. For each pair connected by the optimal, if a set cuts that pair, we have an edge of the optimal solution being colored by the color of that set in the static coloring and the color of the pair in the dynamic coloring. And also for the multi-edge sets, we have two edges being colored. And that gives us this bound for the cost of the forest edges in the optimal solution. For the unconnected pairs, we pay their penalties, which are at most as much as the dynamic coloring done for those pairs, because the dynamic coloring for each pair is bounded by the penalty. So we also get this. And this gives us this bound for the total cost of the optimal solution, which compared to previous analysis in previous works, has this extra term here, which is based on our use of the multi-edge sets that color two edges of the optimal. So then we found the first solution that we get. We can use the same analysis that Iman mentioned for the Steiner forest to argue that the forest selected by our algorithm has cost at most 2 times the total coloring time. And the penalties that we pay penalties for tight pairs. So these two terms are exactly the sum of penalties for the pairs that we don't connect. The total coloring time and the penalties are the same. So we have this, and this is again less than the total coloring time. So we get that this is a 3 approximation. And also based on the bound we had for the optimal solution, we can get this based on the information here. Now we consider the reduced instance that we get our second solution from. And here we set penalties for the pairs that do not connect to 0. So we no longer need to connect those pairs. And we consider what the optimal solution cost for this reduced instances. We try to get a upper bound for this optimal solution using a lower cost solution that we construct using the optimal solution in the original instance. So from opt, we have some penalty. Let's say we start with the first given by opt and consider that as a solution for this reduced instance. We no longer have to pay the penalties for these pairs that the optimal solution paid penalties for, because their penalty is set to 0. So that reduces our cost in this solution for the reduced instance. And we can also remove some edges that only connect pairs that were connected by opt and not by our solution, because we no longer need to connect them as the penalty for not connecting them to 0. So for the second part, we can see that we want to show that we can remove some edges incident to single cut sets. So if we have a single cut set that cuts a pair in this set, based on how we reduced our tightness, there will be, and we assume that there's some amount of dynamic coloring done on this set for this pair, but yeah. Based on how we reduce our tightness, there will be no pair in CC that is cut by this set, because otherwise we could have made this pair not tight and not in our set of pairs that we pay the penalty for. So there will be no pair in CC cut by this set. And also because this is the single edge of opt incident to this set, removing it can only affect the connectivity of pairs that do cut this set. So since it doesn't affect any pair in CC, we can safely remove this. And now we get this amount reduction because of no longer having to pay penalties for these pairs. And based on the removal of edges incident to single cut set that we discussed, we can reduce the cost by this much. So we get that the optimal for a reduced instance is at most this amount. Okay. Now we use induction based on the number of penalties that are not zero, basically, to prove that our algorithm produces a 2 approximation. Our base case is when we have no penalties paid in the first place. So we just immediately return a solution. And we argued that the forest that we choose in the first solution has a cost at most 2 times the optimal. So when no penalties are paid, we just get a 2 approximation. Now, for the induction step, we have our cost of second. The cost of the second solution can be bounded using the cost of the optimal for the reduced instance using our induction hypothesis. So it's 2 times that. And this is the cost of the solution we get for the reduced instance. There's an upper one for that. And we also need to add back the penalties that we set to 0. So we get this additional term, and this gives us this expression, this upper bound for the cost of the second solution. And we had this other upper bound for the cost of the first solution. And the minimum of the two, it will be at most the average of them, which we can see is just 2 times the cost of up. So we get a 2 approximation. Thank you for being here.
So is there any work in like the dynamic version of the problem you're saying maybe the penalties that you decided to pay increase over time for the ones you haven't paid?
Question?
Well, I'm kind of curious. So, where will this be presented?
This paper.
Yes.
So we submitted to SODA, this year. So the final decision hasn't arrived yet. Next month, yeah.
So under,
Yeah.
I guess before all worked
Yeah.
on the paper.
Yes, we
Okay, so the best case, if it's accepted to SODA, will all 4 of you give the presentation?
I think we should get this all scoreboard initially.
Yeah, it's a very nice result.
I think, the one thing they didn't, the motivation was not clear at all at the beginning, because this problem, like, calculating the history was, they were considering, I think, 1989, as well, was considering price collecting, over Williamson, and okay, yeah, they were considering Steiner forest, and then price collecting Steiner, like back in 1990. And their paper actually got there, and their main thing essentially was for Steiner forest. So their paper got the test of time started for just listener for this. So that problem was this price collecting the Steiner tree was obtained essentially Goemans, so that it changed a little bit like the HA model, essentially better presentation. And everyone thought that price collecting the Steiner forest, and they don't present it, they say maybe should the same approach should work. It turned out it does not work essentially, and the people worked a long time essentially. The latest one that we mentioned that was paper of me and Hajiaghayi and Jain back in 2006. So that 254, and people all work to get it slightly better than 205. Let alone, and this was the integrality gap as well, cannot be given. And so this was like essentially a big jump that to know the whole gap But this is the thing, I mean, that should be, I mean, presented much more especially. Yeah. People, yeah, these are like a lot of work should be done. But I think, yeah, we'll see what is the best thing.
Let me support one of the things which he said, which was about animations. In talks where you don't have a lot of time, like visual presentations of things are a lot easier to pick up than, you know, let's say written things. It's sometimes, so I don't know, it might be nice to invest a little bit more time in the animation just to get a sense for how the algorithm, you know, develops, I guess.
Yeah, I think it should be essentially no formula. Just everything you should try to keep the intuition, everything like animations and this. People totally understand, not write the formula. They are not reading. They want to read the formula, they just go and read the thing. They don't come to the talk. Yeah, I think that was just some initial. I think the presentation of the paper is much better. Because they didn't actually, it was like one of the papers, there is no comments. Just, there was one person essentially said, okay, maybe this part about this. Hajiaghayi and Jain algorithm talk maybe a lot in more detail. It doesn't matter anymore. That's like, so we just say that. Just in the response, we just thank all of you. We didn't even answer. You know, you submitted to Soda on the.
No, I didn't.
Because they have the evaluation. And the other one, we ask questions or this one,
strong results, so I think.
Yeah, that's the thing that I mean, exactly like the, not even. But yeah, I think the presentation is not that bad. But yeah, so it was good start actually. Thanks for coming.
Thanks so much.
If you don't have any problem.
You spelled Steiner on some of the slides. You wrote Steiner instead of Steiner.
Oh.
That was the only thing I noticed.
Okay.
I can just tell you, I mean, because when I was presenting my talk essentially, people like, what's the problem? No, I prepared all of this. I presented some of them for day, and they give lots of comments on. I was working like a month on that stuff. Like really 1 month, not just a month. Spend a lot of time in this thing. And this is not that level of talk. That should be the same as the people we see. Because this is the nice thing about it is a very simple algorithm, it's a very natural algorithm. So essentially, you just solve the problems. Those that you are pay the penalty, you pay the penalty. Now for the rest, essentially you rerun it. And you may again pay more penalty for this one. So essentially you run the algorithm, you pay some of this time. Okay, that's one. Then among the others, I'll just remove this. For the other, again run it, it's the same penalty. You may pay more penalty for more penalty. It's the second. Then you will do it the third one. And you will do it until when you run it, it's still the same. Nobody like that's connected, it's still the same technical connect. So if you repeat that does not, you repeat until the solution does not change. Right. And you take the minimum. That's essentially the situation. That's a very nice thing. You don't see the patient here that is like that. This is the solution essentially. This is like very practical thing. This is because if you solve this problem, you generally need to also have a natural algorithm. It's not the case. But the people tried a lot of different things. Interesting, like they tried like iterative rounding, BMSP one there. Lots of approaches, all they become 3 approximations. Right. And so you need to say why you overcome essentially over the barrier. They should see essentially that. And this algorithm is different from this very natural algorithm, but the analysis one that we are doing in the paper.
Yes. Yeah. Okay. Thanks everyone for coming. Yeah.